This will be a very brief video that's just tying some things together from throughout the course, and we'll talk more in person about them. Okay, but the first thing to highlight is that linear algebra is its own beast, its own genre of math course. So there's many different little things that could be included in a linear algebra course. And anyone that teaches it is going to make their own choices of what they put in. There's some things we just simply didn't encounter, that they just never presented themselves. One is the transpose of a matrix. And this is a very simple operation where, let's take this matrix for example. I'm going to take the transpose of it, so I write a little exponent t. And all it is flipping along the diagonal. So I interchange the rows and columns. The first row becomes the first column, and the second row becomes the second column. Okay, like this. Now, the transpose comes up whenever we're trying to find matrices of the correct dimensions. Okay, but the way we dealt with that is we just always ensured that they were of the right dimension, and those are the ones we only dealt with. So when we wrote a vector, we were very careful to write it as a column or as a row, depending on the situation. Now with the transpose, you can switch between a column vector and a row vector by just putting that t. And so that's why we didn't encounter it. It's something that we kind of built into our approaches. Now, matrix algebra, we did a bit of this, but not to the extent that we could have. And that's okay, because it's kind of its own field of math, looking at what type of algebraic structures come up when we're doing, or when we're dealing with matrices. So for example, there's all sorts of results we could derive. For example, if A and B are invertible matrices of the right dimensions, then if I try to find the inverse of this, it should look something like this. Okay, and so those are results we could prove and we might use in some examples. But again, kind of not a major component of what we decided to do. And another aspect of the course, a potential aspect of the course, is that there's a variety of procedures and theorems that we could learn that are used to calculate things quicker, or use different matrix decompositions or things like this. And they're certainly out there, but they just didn't fit in with anything that we were doing. So those are just some potential topics that are out there that you can investigate if you ever do encounter them in subsequent courses. Just skip through all my slides here. So if we think back to all the topics that we covered, they're more or less all here. Remember, we started with systems of linear equations and looking at solutions for these. This is something that's very common in middle school. And what we did differently is that we transformed these into coefficient matrices, and we worked at this level, and then we're able to solve the corresponding system of equations. But then we isolated these for their own right and started studying these matrices and looking at properties of them, thinking of them in different contexts, like it might be a transformation of the plane, with various shearing and stretching and all that. And then we looked at subspaces of these transformations and how it changes the direction of things and how it stretches things out. And then we also found eigenvalues and eigenvectors, and these are thought of in a variety of ways. We saw them in a few different settings, like in terms of long-term stable proportions of in age or stage-structured populations, steady states in a random process of going between happy and sad, for example. They're also invariant directions under the transformation, if you think of it as a geometric transformation. And this eigenvalue is how much the directions are being stretched. So the interesting thing for me in linear algebra is that all of these things are so closely related that there's no wonder why linear algebra as a subject came out of it. We keep on encountering matrices in different contexts, but they follow all the same fundamental principles, and that's really interesting. Okay? And really the last big result that we need to cover, which you're probably seeing from a mile away, is that these really are, all these different aspects of matrices really are the same thing in different guises. Okay? So we have, for example, if we have a square matrix, that system of linear equations, this here has exactly one solution. Okay? So that statement is equivalent to saying the matrix A is invertible, and that's, of course, if we can find the inverse of A, then we can also do this multiplication and it would give us the solution X. So you see how those are related. None of the eigenvalues of A are 0. That's a little bit more opaque where that comes from. But you could imagine that, I'm going to draw some funny axes here, that A, if it transforms a space and it collapses that space down, then that original unit square in that space goes down here to volume 0. And remember that the volume of that unit square under this matrix transformation is the product of the eigenvalues of A. So if this goes down to 0, it's this situation that we collapse the plane like this from 2 dimensions to 1 dimensions. And so I can't undo this. Because I don't know where the square is on this line. It disappears. So I can't find an inverse for A. And so that happens whenever we have an eigenvalue of 0. Okay? Which means if we did have one of 0, it would not be invertible. So you see how those two are related. Okay? Same thing here. A null space of A is strictly the 0 vector. That means that our space isn't being squished under A as a transformation. Okay? Similarly for the identity matrix and the determinant, also we know that the determinant is the product of the eigenvalues. That's not 0. And we saw that in a few different contexts. One is the change in area of this unit square. The other is the invertibility of A, okay, because we use the determinant in that calculation. Okay? So the interesting thing for us really is that all of these aspects of matrices in linear algebra are very closely related. And we can think in terms of pictures and in terms of algebra, in terms of systems of equations, that types of thing, and really be talking about the same thing in those different contexts. Okay? And what we'll do when we meet next is we'll work through some of these problems where we take one perspective on matrices and try to get something out in another direction involving those matrices. So we try to show that these results are very equivalent and that they're all related.